Welcome all. I am Phani Krishna, Faculty of ACE Engineering Academy. Today in this session, I will be providing solutions for ISRO PYQs. Subject is microprocessors. So this is only 1 hour session, right? So without wasting time, without any delay, let's start with the questions. Few questions, mainly focus is on ISRO PYQs. Few questions are on from previous PSU exams, right? Let's start. A 8-bit microcontroller has an external RAM with the memory map from 8000 hexa to 9FFF hexa. The number of bytes this RAM can store: 8193 bytes, 8192 bytes, 8191 bytes, 8000 bytes. Please understand, it looks like it is a question on microcontroller. It can be either microcontroller or microprocessor. A microcontroller, as all of you know, it has its own internal memory. So what they are saying that external RAM is connected. Starting address is given, that is 8000 hexa, end address is given 9FFF hexa. They are asking the size of the memory. Let's see how to solve this. What is the given data? That is the RAM given, right? First byte to last byte. Content is not given. What is the information given to you? Starting address and end address. What is the starting address? 8000 hexa is the starting address. Address of the first byte. 9FFF hexa is the address of the last byte. So what you are going to find out? First, to find the byte difference. Byte difference doesn't mean that we are going to subtract the content of this memory location from this memory location. It can be any content, please. We are going to take the difference between these two bytes. This we call it as a byte difference, right? Let me calculate. What is the byte difference? How you are going to calculate the byte difference? End address minus starting address. Address of the last byte minus address of the first byte. What is that given? 9FFF hexa. Sometimes I will write hexa, sometimes I don't. Minus, what is the starting address? 8000 hexa. Right? In hexadecimal, it is 1FFF hexa. That is the difference between both bytes. You add 1 to this, you will get the size of the memory. They gave it like RAM, so what is RAM size? RAM size is whatever with the byte difference, you add 1. What is the byte difference? Byte difference is 1FFF hexa plus 1. That gives you 2000 hexa. This looks like address. 2000 is not address. 2000 is number of bytes in hexadecimal notation. Options you have seen, 8191, 8192, 8000, that is in a decimal form. So you need to convert this number, which is not in binary, that is not binary, right? Mind you, this is in hexadecimal. Please convert that into decimal. So what is this position values? Not 2 power 0. For binary to decimal, we will use 8421 coding. 2 power 0, 2 power 1, 2 power 2. This is hexadecimal, so this position value is 16 power 0, 16 power 1, 16 power 2, 16 power. So 2 into 16 power 3 plus 0 into 16 power 2 plus 0, 16 power this plus 0. All these are going to be zeros. Let's calculate what is 2 into 16 to the power of 3. 2 into 16 to the power of 3. If you calculate, you will find it as 8192 bytes, not bits. This memory has 8192 bytes, 8192 bytes. How that is organized is a different story. In different ways, this information can be given. I am continuing further. 8192 bytes is the answer. Anyway, B stands for not bits, B stands for bytes. Or in terms of kilobytes also it can be given. What is 1 kilobyte? 1 kilobyte is 1024 bytes. So 8 into 1024 bytes. You can also write like this. That is 8 KB, 8 kilobyte. 1 kilo is nothing but 1024 bytes, right? So you can also write it as 8K by 8 bits. In different ways this can be mentioned to you, right? Okay. So we will see what is the answer given to 8192 bytes. 8192. Please read this question, try to understand. A 8085 microprocessor based system uses 4K by 8 RAM whose starting address is AA00 hexa. What is the address of the last byte in this memory? In the first question, starting address and end address is given, they asked the size. In a different way, this is formed. What is the information given to you? 4K by 8 RAM and the starting address is AA00 hexa. End address is asked. Let's do this. What is the given data? That is the RAM given to you. Let it be ROM or let it be RAM. If it is ROM, no, it starts from 0000 hexa, right? First byte, last byte, starting address, end address. What is the starting address given to you? AA00 hexa. Obviously, RAM cannot start from 0000. ROM starts from 0000. What is the size of the memory? Size of the memory is 4 kilobytes. What is asked? End address is asked. Now, how you are going to find out the byte difference now? I normally tell you a trick in the classroom, not a formula. Byte difference can also be calculated as n ones, where n is the number of address lines of that memory. Trick, not a direct formula. Byte difference is basically end address minus starting address. This is another way. So, we will try to calculate how many number of address lines are there for this given IC. What is the size of the memory given to you? 4 KB, right? 4 KB and 2 power 2 by 2 power 10 bytes. That is 2 power 12 bytes has how many address lines? 12 address lines. Is it not? This is what normally we start with. This is the statement. If a memory IC has a n address lines, then size of the memory is 2 power n bytes. So 4 KB is 2 power 12 bytes. It has 12 address lines. If you want to represent them, A0 to A11 is the representation. So what is its byte difference? Byte difference of 4 KB is 12 ones. 12 ones and we try to represent in terms of hexadecimal. So from the LSB onwards, while writing itself, let me group 4 ones. 1, 2, 3, 4. That is F hexa in hexadecimal. 1, 2, 3, 4. 1, 2, 3, 4. From LSB onwards, I will group, not from MSB side. So what is this number in hexadecimal? F hexa. Normally, everyone knows 4 KB means the byte difference is FFF. What are with the starting address and end address? Earlier 8 KB na 1 FFF. The same manner, these are standard sizes and standard byte difference. But that is not the answer. They are asking about the end address. So what we know now, we know the starting address, we know the byte difference. So how you will get the end address? What is the starting address? Given data. Starting address is AA00 hexa. What is the byte difference I calculated as per given data, that is 4 KB? FFF hexa. Please add these two, then you will get the end address. That is the end address. In hexadecimal you can do. You want to do it in binary, you can do in binary. That is up to you. This is 0 plus F is F, 0 plus F is F, F plus A. F plus 1 is 10, remaining 9. So it is 19. 19. A plus 1 is B, B9FF hexa. B9FF hexa is the end address. It is starting from AA00 and set to B9FF because there are 4 kilobytes. Answer is option B, B9FF hexa. Let's see the next question. Please read this. A 8085 microprocessor based system uses 8 K by 8 ROM, 8 KB ROM, simply you can say 8 KB ROM and a 16 K by 8, that is 16 KB RAM ICs, 2 memory ICs. Considering continuous memory address mapping, the end address of the last byte is. 2 memories, obviously in any microprocessor based application, 2 memories will be there. One is read-only memory, another one is read-write. Read-write memory or random access memory, any term you use. So what is the given data? Let's look at this given data. 8 KB ROM is given and 16 KB RAM is given. What is asked? No other information is given. Please observe, no other information is given. This is the starting address of ROM. which is normally going to be 0000 hexa because it is ROM. This point you have to understand. In 8085 based system, ROM has to start from 0000 hexa because that is the number which gets loaded into program counter when reset signal is applied. Not in every processor, I am talking about 8085. So, we know the starting address of ROM, we calculate the end address of ROM. Then what about the next address? This information is given now, here, you see, continuous memory address mapping is used. RAM is going to start immediately after ROM. So, it starts whatever be the next address, then we calculate this. No other information is given, only sizes are given. So, let us start with this 8 KB ROM. 8 KB, what you can calculate from 8 KB given size, number of bytes is fine. Address lines you can calculate. What is this? 8 and 2 power 3 by 2 power 10 bytes. That is what? 2 power 13 bytes. 2 power 13 bytes memory, let it be ROM or RAM, that is not the point, has how many address lines? 13 address lines. 13 address lines. What are they? A0 to A12. If you are interfacing this memory IC to 8085 microprocessor, out of 16 address lines of 8085, you have to use only these 13 address lines for byte selection. Remaining upper order 3 address lines, you are going to use them for chip selection of the same chip. So, when you know that it has 13 address lines, so immediately what you can conclude? What is the trick? Just now I did in the previous question. Byte difference of this 8 KB is equal to 13 ones. 13 ones. It's a trick, it is not a formula, right? As we do so many problems, right? We use this trick. So, please write and group them. While writing itself, you group them from LSB onwards, not from MSB. You will go wrong. So, 1, 2, 3, 4, F hexa, 1, 2, 3, 4, F hexa, 1, 2, 3, 4, F hexa, 12 ones, one more one. So, already we did in the first question. What is the byte difference? Byte difference is for 8 KB, 1 F hexa. This byte difference, this difference is 1 FFF hexa. 1 FFF hexa means, what is that starting address of this ROM IC? 0000. Hexa, not 4 bit, 16-bit number. Why? Because it is ROM. Not because it is 8 KB. ROM always has to start from 0000 in 8085. What is the byte difference? Because it is 8 KB, we calculated it as 1 FFF. Let me write what is the reason it is 1 FFF. 8 KB. Any other size can be given. So, you add the starting address and byte difference. You will get the end address of that memory. What is that number? 1 F hexa. So, 0000 hexa to, let me write in the next page, 0000 hexa to 1 FFF hexa is a address range or address space of this given ROM. So, now we want, what we want? We want the end address of this na. So, what about the 16 KB RAM? Let me start 16 KB, same way. Let it be 16 KB, let it be 32 KB. Maximum you can connect 64 KB memory, both including ROM and RAM. Not 64 KB ROM and 64 KB RAM, right? Combinedly it is going to be maximum 64 KB, since that is the addressing capacity of 8085 microprocessor, as it has got 16 address lines. You know all this, right? You are supposed to know. That is a prerequisite to understand. 16 KB means what? 2 power 4 by 2 power 10 bytes, right? 2 power 14 byte memory means how many address lines are there? 14 address lines. What are they? A0 to A13. So, as this memory IC has 14 address lines, what is its byte difference of 16 KB? 14 ones. Please write down 14 ones and tell me the byte difference. Please group them 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That is 12, 13, 14. That is in 8421 coding, it is 3 F hexa. The byte difference of this is 3 FFF. If you know the starting address, you can add the byte difference and you will get the end address. What is the starting address of 16 KB? Is it given? It is not given. Are you going to take any conclusion? But one more point is given. What is that point? Continuous address mapping. This is ending na 8 KB ROM. Just now we calculated that it is ending at 1 FFF. So this is going to start from where? This is going to start from 4000 hexa. Sorry, this is 3 FFF. This is going to start from 2000 hexa. This is a 3 FFF is a byte difference. 8 KB ROM is ending at 1 FFF. So what is the starting address of RAM IC? 2000 hexa. So what is the byte difference? Byte difference is 3 FFF. You add these two, that becomes the end address. What is end address? Directly you can do. There is no need to convert it into hexadecimal. 5 FFF hexa. This number is 2000. Because just now I calculated 3 FFF na, so in hurry I wrote 4000. That is wrong. 2000 to 3 FFF is a byte difference. So this is going to end at 5 FFF hexa, 16 KB RAM IC. That is the answer. Five FFF hexa. Option A is the answer. Let's see one more. Please read this. A memory system of size 16 KB is required to be designed using memory chips which have 12 address lines and 4 data lines each. Then the number of such chips required to design the above memory system is dash. 2 chips, 4 chips, 8 chips and 16 chips. What is that given data? You see 2 points are given. This is a requirement, required size of the memory you want to design. This can also be considered as a digital question, not exactly like microprocessor. Anyway, so this is the required memory size. This is what you want, large size memory. Using the available chips. Available chip size is not directly given. What is mentioned to you? About the number of address lines of that memory IC available, small chip. And also number of data lines. Normally 8 data lines. Now they are considering 4 data lines. Okay, take it. Let me write that point first. What is given data I am writing? Required size. Let it be ROM or RAM. What are be the required memory size? What is the required memory size? 16 KB. What is the meaning of 16 KB? 16 kilo locations are there where each location width is 8 bits. But you don't have that kind of chip. What is the available chip? Available memory chip. Small chip is there. Is size is given? Size is not given. Then what is given? Number of address lines are given. How many address lines? 12 address lines. How many data lines? 4 data lines. That is the information given. 12 address lines and 4 data lines. So when 12 address lines are there, 2 power 12 locations, where each location is of 4 bits. Small chip is. Question is, how many such chips are required in order to design this memory? Let's call that number as n. 1, 2, 3, 4 like that. How many are required? Let's call that as n. How they are going to be connected is a different thing. You will study that in memory organization. No one is asking you to draw the memory organization here. So how you will get n? Requirement by availability. N is equal to required size by available size. What is the required size? Let me do here. Required size is 16 KB. What is the available size? 2 power 12 by 4. So how to write 16 KB? 2 power 4 by kilo is 2 power 10. Bytes is 8 bits by 2 power 12 by 4. That is 2 power 14 by 2 power 12. I need not write another step. So 2 power 14 minus 12 is how much? 2 power 2. 8 by 4 is 2. That is 2 power 3. Means what? 8. 8 such chips are required. How they are going to be organized? That is a different story. That is what you learn in digital, in memory organization. Right? Not memory interfacing. This is not truly a question on microprocessors. But normally we see these kind of questions in DRDO, in GENCO, in ESE exam, right? So just added it. It's not about interfacing, it is about memory organization. So 8 such chips are required. Let's see the answer. C, option C. One by one, see I am not giving you any data here, right, theory part. This is 1 hour session, no, just directly I will be solving, reading the question and I will be solving the problem. Let's see next one. Please read. A microcontroller differs from a microprocessor in terms of dash. You studied na, about microprocessor and microcontroller. Let's look at the options first. What are the options given? Option A, I/O interfaces and instruction decoding, memory configuration and I/O interfaces, data bus width and clock speed, memory configuration and instruction decoding. See, what is microprocessor? What a microprocessor consists of generally, you take the example of 8085. What a general purpose microprocessor consists of? 3 building blocks, as all of you know. One is known as control unit, another one is known as ALU, and another one is known as register unit. Either you call register unit or you call it as register A. No other element, control unit, ALU and register unit. I am not explaining here. Any memory is there inside a microprocessor chip? No memory. This is the microprocessor, na? No memory inside. As there is no memory, we are going to connect an external memory, ROM and RAM. We will connect it to 8085 via suitable memory interfaces. Any I/O interfaces are there? What do you mean by I/O interfaces? Ports, I/O ports. I/O ports are not there. 40 pins are there. You studied the pin diagram of 8085, 8086 also. Where are ports? No ports. So if you want to interface any device to the microprocessor, like a LCD, keypad, there is no port to interface. So we require in between the microprocessor and I/O devices, a I/O interface chip. Best example is 8255. Okay. Then what is a microcontroller? A microcontroller is nothing but same processing unit. Control unit will be there, ALU is there, register unit is there, along with the inbuilt memories, both the data memory and code memory, and also I/O ports, and also some control features. For example, a timer and counter is one of the examples of control features. When control features are there, to manipulate them, special function registers are required. Tmod, Tcon for manipulating timer counter configuration. So that is the statement I gave. A microcontroller is nothing but a processing unit. This is the processing unit. Inside this processing unit, you will find the control unit, register unit and arithmetic logic unit. General purpose registers will be there inside this processing unit. Along with what? Inbuilt program memory, code memory, instruction store, anytime you use inbuilt data memory, and also inbuilt control features which are not there in general purpose microprocessor, like timers and counters. And when control features are there, to manipulate them, you require SFRs. Timer counters are there in 8051. To manipulate them, you have Tmod register and Tcon register. And parallel I/O ports are there. No parallel I/O ports in 8085. If you see 8051 microcontroller, you people might observe port 0, port 1, port 2, port 3, and obviously a serial port. Serial port also exists in some microprocessors, right? That is not a point, but in general. But manipulation of serial port may not be available in a. So if you compare these two, how they are differing? Not in terms of instruction decoding. In the given options, in 2 options instruction decoding is given. Why this will not decode instructions? Work of this is also same. It is nothing but a processing unit. So that will decode, this will decode once instruction is fetched. So how they are differing? They are differing mainly in terms of memory and I/O. And in another option, I think data bus is given, clock speed is given. Clock speed is also they are differing. But data bus, 8085 is 8-bit processor, 8051 is 8-bit microcontroller. Both are said to be having 8 data lines. Okay. Clock speed they differ, but main answer is B, memory configuration and I/O interfaces. They said I/O interfaces, that is I/O ports. Right? Let's see one more question. In the context of 8085 microprocessor, the correct matching combination between column A and column B. Achha. It's a JTO question, I just added some extra questions, right? What is column A? ALE is given, PSW, CMA, RLC. And column B, please read column B. What is given? Several statements are given. Just you read. Now what ALE stands for? As all of you know, ALE stands for address latch enable. ALE is a signal, address latch enable. It is used for demultiplexing the multiplexed address data buses of 8085. So where is ALE, address latch enable? Not arithmetic logic enabled, address latch enabled. So P matches with 4. No explanation, directly I am telling. What is PSW? PSW stands for program status word, which is a 16-bit register pair of accumulator and flag register. Don't compare with 8051, we are talking about 8085. In 8051, the flag register name itself is PSW. Okay, where is program status word? Here program status word is there. Here program stack word is also given, right? It is not stack word, program status word. So Q matches with 3. What is CMA? CMA stands for complement accumulator. It is an instruction. This is a signal pin, output pin via which a signal is generated. This is a register pair name, right? And this is an instruction, CMA, used for complementing the number that is there in accumulator. Where it is complement accumulator, not compare. Some people also confuse it with compare accumulator. It is a complement accumulator. So CMA matches with that 3, option R matches with 7. RLC, rotate accumulator left, very clearly given RL. But here if you observe in the options, where it is, here, rotate accumulator to left is mentioned. In the end you see, rotate accumulator to left through carry, Here I think it came, no, somewhat it got adjusted. That is not matching with my system. Carry, through carry. Please understand, RAL instruction is there, RLC instruction is there. Later in the program question also we will see once. Whenever C alphabet is there, we don't include the carry in rotation, right? If C alphabet is not there, we include the carry in rotation. So RLC, rotate accumulator contents to left, not including the carry. So 4, 3, 7, 1. That is I think option 4 is given here, 3 here, but it is 2. That is wrong, right? Here also it is 8. That is wrong. 4, 3, 7, 1. So option is C. Option is C. Let's see another question. 8085 microprocessor program uses all available jump instructions. No one will write like that. Who will write a program that contains only jumps? They are testing you. Who will write all available jumps? Okay. So each only once. For this program, the total memory in bytes occupied by the jump instructions is dash. 30 bytes, 24 bytes, 27 bytes and 18 bytes. Tell me what is a jump instruction? Jump instruction is basically a branch control instruction. Jump, call, return. I don't want to explain because it is about number of bytes. This is the syntax for jump instruction. Example, JMP 0845. Opcode is JMP, converted into machine code, will be decoded later by the processor. 45 is a lower order byte of the address. 08 is a higher order byte of the address. So you ask me what is this? I will say this is one unconditional jump. Where address is given, what is that address? That address is known as a target address. Okay, that is a target address. One unconditional jump instruction. You can give here address or you can give label. Jump delay, jump sum. Some label can also be given here. You are not supposed to use keyword. You are not supposed to use keyword, right? Right. But there are other jumps also. What are other jumps? 8 conditional jumps are there. Out of the 5 flags in the flag register, except the auxiliary carry flag, remaining 4 flags, carry flag, parity flag, 0 flag, sign flag, all these 4 flags can be tested against 0 or against 1 for jump operation. So you see here I am showing jump on carry, jump on no carry, different addresses I have used. Jump on parity even, I used a label now here, jump on parity odd. Jump on 0, jump on no 0, jump on plus, jump on minus. There is no jump on auxiliary carry and jump on no auxiliary carry. Auxiliary carry flag is not testable here. It is tested only in one instruction, that is known as DAA. You know, I think in DAA instruction execution, internally auxiliary carry flag is tested along with the lower digit of accumulator. So my point is, I have seen people, they don't consider this, they remember all these jumps, right? How many jumps are there? 8 conditional jumps are there. What is the length of each jump? And 3 bytes obviously. So 3 into 8, 24 bytes. Wrong answer, because no, you are missing this. This is a unconditional jump is also there. So here these 8 are conditional jump instructions. These are 8 conditional jumps are there. Right? What is the length of this into 3 bytes? What is the length of this into 3 bytes? So this value is 3 bytes. This is 24 bytes. If you miss this point now, you remember that normally people go through the tables. 8 conditional jumps are there, 8 conditional calls are there, 8 conditional returns are there. They remember only about these. Okay, but this is also there na. So total, how many bytes? 27 bytes it takes. No one will write a program. And another point, these are the labels please. Even if label is given, any kind of label except a keyword you can use, not lengthy, 4 or 5 letters you can use. Please understand, when you write a program now, you will use an assembler to assemble the program. The assembler software will replace this label with the target address. Normally we write instructions like this. We also write using addresses, but this is a better way of writing, using labels. That label is a label of an instruction where you want the processor to jump. So how many total? 27 bytes. 27 bytes. Okay. Let's proceed with the next question. Please read. Just read for once. The content of the memory location 2070 hexa after the execution of the following 8085 program is. A program is given. Normally this is how objective questions are framed. You need not write a program. It is not like in college. In college you are supposed to write a program, go to lab, you execute the program, see the output, all that you need to do. You need to remember all the instructions there, right? Even in the end exam, either theory end exam or lab end exam, you need to remember. But here not required. When particular program is given, few lines will be there. You must be able to understand what is the execution. That is more than enough. Some logic will be there. That logic you need to catch. Particular program won't be there. In college, write a program to find the sum of the first 10 natural numbers. Standard programs will be there, right? If there is no particular logic, they will give some logic. So one by one we are going to execute all these instructions. This is the program where you can see subtraction instruction is there, ANDing is there, data transfer instructions are there. So let's execute this. LXI B, 2070 hexa. Please understand, that is initialization. First 3 instructions are initializations. We are initializing accumulator here, we are initializing C register here, and we are initializing a B register here, BC pair. Let's not take BC pair. I think one small mistake is there in this program. That mistake is, this is not given, no, fine, but I think they made a small mistake while typing. You see, when you initialized here BC pair, again you are reloading C register. That is not to be done. So we will keep C because we are subtracting C, and finally we will try to store now. Here we don't put C, we will put B here. Not BC pair, we will put a DE pair. We will take DE pair. The mistake, normally I do this in class, STXD. Because you are subtracting again. Once you initialize a pointer, right, with the required address, again how can you reinitialize it? Meaningless. Anyway, so here what I am going to do, LXID, and that's it, STXD. LXID, 2070 hexa. LXID means what? A DE pair is initialized with 2070 hexa. MVI A comma 8F hexa. What do you mean by MVI? Move immediate. You are going to initialize the accumulator with a number, 8-bit number. Accumulator is initialized with 8F hexa. MVI C comma 68 hexa. This is what I am saying. If I keep this as a BC pair is initialized with 2070. Now we are again changing it. That is not the correct way, because finally this address will not be matching, right? This is basically a typing mistake done. I got corrected. So C is initialized with 68 hexa. 3 initializations. In any program, now this will be there normally. Registers are to be initialized. So initialize them. Then what? Sub C. Sub C means what? Subtract C. Means subtract C register content from whom nothing is mentioned. You know, you are supposed to have the understanding of instruction sets. In 8085, it is accumulator based ALU. There is no need to mention about accumulator. From accumulator, we subtract C register. A result is stored back into accumulator. What is there in accumulator? 8F is there. What is there in C register? 68 is there. So 8F minus 68 is performed here. Who is going to perform? ALU of 8085. But please understand, this 8F minus 68 is performed in a 2's complement form. I am doing it here. 8F hexa minus 68 hexa done as using 2's complement technique. 8F hexa plus 68 hexa bar plus 1. What is this 68 hexa bar plus 1? That is a 2's complement of that. So we are supposed to find out this, then we will do the subtraction. Let's say D and this is D. What is it? Take 68 hexa 0 1 1 0 1 0 0 0. Complement it. What complement? 1's complement. 0 becomes 1, 1 becomes 0. You also do 1 0 0 1 0 1 1 1. Add 1 to it. 1 plus 1 0 1, 1 plus 1 0 1, 1 plus 1 0 1, 0 plus 1 is 1, 1 0 0 1. What is this number? 98 hexa. Means what? Minus 68 hexa. 98 hexa is minus 68 hexa in a 2's complement form. Please understand, later if any negative result is formed, negative result cannot be stored in accumulator as it is. It is always stored in this way, 2's complement form. Minus 1, suppose result is minus 1, assume in some example. How minus 1 can be stored in accumulator? It cannot be stored. Minus 1 will be stored as FF hexa. So, this 68 hexa, this one, 8F hexa minus 68 hexa is actually done as 8F hexa plus 68 hexa bar plus 1 is done as 8F hexa plus 98. This is how you are supposed to do. 2's complement technique. This is D, this is D. So do this 8F hexa plus 98. 8F hexa plus 98. Whatever you get, the result will be stored into accumulator. Do it. 1 0 0 0 1 1 1 1. 98 hexa 1 0 0 1 1 0 0 0. Please do the addition and write down the flags also. 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1, 0. This is known as auxiliary carry. The overflow from D3 to D4 is known as auxiliary carry, will be stored in the auxiliary carry flag, in the flag register. So 1 plus 1 is 0, 1, 0 plus 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1, 0. Again there is a overflow here. This is known as carry. But please understand, in other operations we will take this carry as it is. But in subtraction operation, as ALE is doing this subtraction using 2's complement technique, whatever be the carry obtained will be complemented and then stored in the carry flag. This is also considered as a borrow. Higher number minus lower number we are doing now, we don't require borrow. That is what ALU is supposed to tell. This cannot be 1, will be complemented. 0 say gets complemented to 1, 1 say complemented to 0. And what is this? This is where stored. This is stored in the sign flag, the flag register. And 2 more flags, let me write. One is a parity flag and another one is 0 flag. Don't count for parity those carry and auxiliary carry. These are the 2 overflows. How many ones are there in the result? 1, 2, 3, 4 ones. 4 ones means what? Even parity. Parity flag is 1. Non-zero result, so 0 flag is 0. So what is the result you got? 0, 0, 1, 0 is 2. 7 hexa. 27 hexa is the result that is stored in accumulator. Condition of the result like carry flag, that is borrow, parity, auxiliary carry, 0 and sign. That is a sequence will be stored in the flag register. Combination of these 2 registers is known as PSW, as I told you earlier. But what is the next instruction after sub C? Accumulator content is 27 hexa. ANI 0F hexa. What ANI stands for? And immediate. This is move immediate, this is load immediate, this is and immediate. So whatever is there in accumulator, 27 hexa is ANDed with given number, immediate operand. This is not immediate, this is register, this is immediate. Immediately available for the processor in the instruction itself. What is that number? 0F hexa. And where the result is said to be stored in accumulator. I think you can directly tell, right? 7 ANDed with F is 7 hexa. 2 ANDed with 0 is obviously 0. I am not writing any flags. STXD, now not STXB, because they asked content of a memory location 2070. C got changed to 68, right? So I changed it properly, right? I corrected the error in the program. STXD. STXD means what? Store the accumulator content. This is D. Store the accumulator content into a memory location whose address is available in DE pair. The beginning you have seen now the DE pair got initialized with 2070. Let me symbolically write this. Store the accumulator content, that is 27 hexa, into a memory location, RAM location, whose address is available in DE pair. This is how I write normal. Content of DE pair. What is the content of DE pair? In the beginning it got initialized with the 2070. So inside DE pair 2070 hexa is there. That is the address into which what is there in accumulator content? You got as 27 or 07? 07. So 07 hexa will be written into this location. Okay. Then processor gets halted as it executes the halt instruction. And how 07 hexa will be written? As you know, I always give example, right? This 3 buses, because it is there, that operation. What is this operation known as? This operation is known as a memory write operation. Just I am giving an additional point. Whenever memory write operation is performed, 8085 will use 3 buses. This is address bus, this is the control bus, and this is the data bus. My left hand is my data bus, my right hand is my control bus. One control signal will be generated. What is to be written? Data is to be written. What is the data? 07. Into which location? Location number 2070 hexa. So out of these 3 buses, which bus will be used first? Address bus. If that is location is a student, now I will generate roll number, that is a roll number 2070. So I will send address first, then I will send data. What is the data? 07. Then I will generate a write control signal. 3 clock cycles are required. My left hand is my data bus, right? This is my control bus and this is my address bus. Always remember 3 buses, 3 micro operations, 3 clocks. Yeah, one extra randomly I added. So what is the answer? Answer is 07. They asked what is the content of that location 2070. So content of that location is going to be 07 hexa. One more. Please read this. Consider the following program for 8085. XRAA LXA comma 0007 hexa, DCXB, JNZ loop. Small program, 1, 2, 3, 4 lines are there. The loop will be executed. Loop in the sense what? These are the 2 instructions that are inside the loop. Loop is a label given here. In 8086, now loop itself is an instruction. Here loop is a label, right? Loop will be executed how many times? 8 times, once, 7 times, infinite times. Let's do this. Yeah, that is a program given. One by one, this is what you are supposed to do. One by one, you are supposed to execute the instructions. If your logic is matching properly, it is working out, then your execution is happening, then you will get the correct answer. Let's see, XRAA. I think the number in accumulator is not given, so I am assuming some number in accumulator, 45 hexa. Normally in the classroom, I take 45 hexa in accumulator. Same number, let's take. Accumulator is initialized with 45 hexa. What is that XRAA stands for? Can you XOR accumulator with accumulator? Normally we XOR accumulator with a B register, with a C register, but you can also XOR accumulator with accumulator. What happens there? Accumulator content, that is 45 hexa, just I took this number, is exclusively ORed with the same accumulator 45 hexa. Result is stored back into accumulator. 1 minute. Please do this. Do this accumulator content 45 is XORed with 45. I think you know 1 XORed with 1, output will be 0. 0 XORed with 0, output will be 0. So what will be this result? 00 hexa, very popular instruction for resetting the content of accumulator. 0 flag will be set to 1 and other flags are also affected. I am not writing all of them because here I can see JNZ instruction. As the accumulator content reset, very popular instruction to reset the accumulator content at any point of the program. Okay, 0 flag is set to 1. So what is that next instruction? Next instruction is I am writing in the next line, right? Okay, extra space is not there. Okay, what is that? LXI B comma 0007. LXI stands for what? Load immediate. So that B should be considered as a not 8-bit B but 16-bit BC pair. If it is given as MVI B, then we take that B as 8-bit B register. As it is given as LXI, we consider it as 16-bit BC pair. What is BC pair content? Loaded with 0007. But point is, you need to understand, this instruction is a data transfer instruction, not going to affect the flags. Flags are affected for execution of the arithmetic and logical instructions. So, what 0 flag? What is the effect on the 0 flag immediately after this? Same, it is going to be maintained as same. What DCXB will do? DCXB. Is it DCRB or DCXB? DCXB. You initialized a 16-bit register and you are decrementing 16-bit register. What is the instruction for decrementing 8-bit B? DCRB. DCRB, INRB for incrementing, decrementing 8-bit registers. They are done by 8-bit ALU. This is not done by 8-bit ALU. First of all, what is the operation? It takes the content of BC pair 0007 hexa, decrements by 1. So what is the result? 0006 hexa. But again, please understand, this also is not going to affect the flags. Alright, it is arithmetic instruction, na? It is arithmetic instruction, not done by 8-bit ALU. Why cannot do? This is 16-bit number being decremented. This is 8085 processor. This is a kind of special instruction. 8085 ALU is 8-bit ALU. It can do 8-bit operations. It can increment 8-bit number, decrement 8-bit number. It can add to 8-bit numbers. It can subtract, you have just now seen. It can subtract one 8-bit number from another 8-bit number. This DCX, INX operations are not done by 8-bit ALU. They are done by a special circuit, that is incrementer / decrementer. Observe the architecture diagram. Below to register A, you will find the incrementer / decrementer. That is the one which will increment the program counter by 1 every time. That is the one which will decrement the stack pointer by 2 in push operations. That is the one which will increment the stack pointer by 2 in pop operations. So same incrementer decrementer will execute INX and DCX. So flags are not affected as ALU is not involved. Means what is the point? After the setting of 0 flag, the next 2 instructions before J and Z are not going to affect the flags. I am writing here 0 flag is not affected. Let me write here flags are not affected. No other flags are affected. Flags are not affected. For what? For LXI and also for DCX. Therefore, 0 flag remain as 1 only. Right? Then what you are doing? What is the next instruction? J and Z loop. What is J and Z? It is a conditional jump instruction. Let me write here. What J and Z stands for? Jump if no 0. That is the meaning of J and Z abbreviation for that opcode. What the processor will do? It will check the 0 flag. If it is 0, it is going to jump to loop level. If it is JZ, jump if 0. Jump if 0 means 0 flag tested for 1. J and Z, jump if no 0 means what? 0 flag tested for 0. Jump if no 0 to where? To loop label. So here, what is the test performed? You are supposed to know Z flag is 0 flag is 0 is a test performed. This instruction is not going to affect the flags. The previous arithmetic logical instruction, previous and before this, these instructions. Actually, this affected flags, this did not affect, this did not affect. So the effect of this only going to be checked here. So is it 1 or is it 0? It is 1. So test failed or test passed? Test failed. Test failed means what? 8085 is not going to jump. I don't have space here to write. Okay, let me do. Therefore, 8085, no jump. Why? Since test failed. First time itself test failed. If test passes, it will jump. Again decrement. That's what happens in DCR. Okay. Anyway, here test failed since 0 flag is 1 as set in the beginning. So this set of instructions, this is executed for once. This is executed for once, this is executed for once, will enter here, cannot jump, so goes. All these instructions which are inside the loop are executed only for one time. Is it not? Only for once. Option is B. But if you enter to the same loop with the 0 flag as 0, it becomes infinite times. It cannot come out of the loop because DCX is not going to affect the flags. If I remove XRA, answer becomes infinite times. Anyway, here answer is once. Let's see one more. Which one of the following statements about the 8085 is true? Please read. Only accumulator can be loaded with an 8-bit number in a single instruction. Is it true? No. Why only accumulator? Already you have seen two questions where once accumulator is initialized, B register is initialized, C register is initialized. You can initialize accumulator, you can also initialize B, C, D, E, H, L, 6 GPRs. So this is wrong. This is not true, false. The processor can be interrupted even after it executes the halt instruction. Correct. That is what the meaning of interruption. Na? When microprocessor is executing the main program, that processor is supposed to be interrupted if an interrupt signal comes externally or internally also. Even after executing the halt instruction, means as it gets halted, then also if you want to bring the processor out of the halt condition, either you apply reset signal or you apply an interrupt signal. This is true. There is no need to check C and D, but we will check. When hold input is activated, the processor can execute register to register instructions. What is hold? It is a DMA request signal. This is the processor, this is the input, na DMA request signal. You are sending 1 to the hold input means what? You are telling the microprocessor to hold. DMA request is assigned with highest priority even than interrupts, compared to interrupts. So whenever DMA request is received by the processor 8085, it will complete current operation. It will generate a DMA acknowledgement, that is HLDA, hold acknowledgement signal via HLDA output, and enters into idle state. All of you know this. Not wait state. It is already in processing state. For hold input activation, after completing the current operation, generates an acknowledgement, it enters into idle state. And when it is in idle state, how it can do register to register instruction? When it is in idle state, the device along with the 8259, sorry, not 8259, 8257 direct memory access controller will access the memory. So this is wrong. The program and data memories are separate. No, they are not separate. 8085 follows von Neumann architecture. The same memory available. Suppose the here to here 0002 0FFF, then 10002 1FFF. In the beginning you have seen in one question, right? The same memory used in von Neumann architecture. This statement is true for any processor that uses Harvard architecture, but 8085 follows von Neumann architecture. So D is also wrong. Answer is B. The processor can be interrupted even after it executes the halt instruction. One more question. The content of the HL register pair after execution of the following program on the 8085R. Small program is given: LXI, LXI, push, XTHL, pop and halt. You have to execute this and you have to find out what is the HL pair content. Let's see, execute. No one will ask you to write a program, please understand. And program is given, you must be able to identify the operation and execute it. Let's do. LXA H, 2095. Question is not on stack pointer content. Question is on what is happening to HL pair content. HL pair is initialized. This is a HL pair. This is a BC pair. So let me write here. HL pair is initialized with 2095 hexa. LXA B, 8FBF. BC pair is initialized with 8FBF hexa. Right? No stack pointer. So I am not talking about stack pointer, but I will mention also about stack pointer, because no same question can be framed where they can ask you what is the stack pointer content at the end. We keep track of the stack pointer also. I hope you know what is push, what is pop, what is XTHL. See, they have given a program where all the 3 instructions of stack related operations are used. Push, pop, XTHL. Okay. What push B? We are trying to push the contents of BC pair onto the stack memory. Content of BC pair, that is 8FBF hexa, is pushed into what? Stack memory. BC pair is a 16-bit number, na? Content is 16-bit number. So how many locations are required? 2 locations. So what I will write here is not any 2 locations in the stack memory. I hope you know about stack memory. Exactly top 2 stack locations. Just I am writing here top 2 stack locations. Top 2 stack locations. What is there in BC pair content? Need not show diagrammatically. Here itself I will write 8FBF hexa. 8F BF hexa. Okay, what is there in top 2? We don't know. XX, some randomly I am writing, some number will be there. RAM, na, it is a part of RAM. So this is pushed here, 2 memory writes. So this number, existing number, is replaced by 8F BF hexa. Please understand, 2 memory write operations are performed. So stack pointer content, whatever be the number, is decremented by 2 for push operation. So question is given no on stack pointer, then also you can follow. Then XCHL, what XCHL stands for? Exchange. In 8085 there are 2 exchange instructions, XCHG, XTHL. In XCHG, HL pair content is exchanged with DE pair. In XTHL, as the name implies, HL pair content is exchanged with the top 2 stack locations. So I am writing here HL pair content, which got initialized with 2095, is going to go into top 2 stack locations, that is pushing, like here pushing, and whatever is there in top 2 stack locations is going to be retrieved back into HL pair. But which one, that is popping, this is popping, that is pushing. Both cannot happen simultaneously. Which one will happen first? Pop will happen. Why pop will happen? Because inside 8085 WZ registers are there. Inside 8085 WZ registers are there. Temporary registers are there. Program invisible. Used for these purposes only. So this push and pop, which is exchange operation, happens via WZ. First pop into WZ, everything I cannot show diagrammatically. First pop, whatever is there in the top of the stack. What is there in the top of the stack? Let me write here 8F BF hexa. What is there in HL pair? Let me write here 2095 hexa. So whatever is there in the top of the stack is taken into WZ. Then obviously from WZ it is going to move into HL pair. When it is moving from WZ into HL pair, content of HL pair is pushed into top of the stack. A sequence of operations will happen. So first pop into WZ, then push HL pair. When it is pushing, it will move the content of WZ into this. So this finally will go here, that is 2095 comes here, that is what exchanging na. And this will come here, that is 8FBF. So push happens, pop happens, that is pop followed by push. Okay. So what is the content of stack pointer for pushing? Incremented by 2 for pop operation. Earlier it for pushing it decremented. Now stack pointer is incremented first for popping, then it is decremented for pushing. So for XTHL instruction, the stack pointer content remain unaltered. So what is there in HL pair now? 8FBF is there. Top 2 stack locations 2095. Then pop H, let me write here itself instead of going into the next page. Pop H. Pop H means what? From top 2 stack locations, whatever is there in the top 2 stack locations, you retrieve into specified register pair. Which register pair? HL. What is there in HL pair? 8FBF. What is there in top 2 stack locations? 2095. So whatever is there in the top of the stack, they have used all the 3 in a line. That nothing, no particular logic here. Push, exchange and pop. Anyway, 2095 that is there in the top of the stack is retrieved, that is popping into HL pair. So 8FBF is replaced by 2095. What is the content of stack pointer, effect on the stack pointer for this popping? It is incremented by 2 for pop. For push, decremented by 2. For XTHL, it remains same. For pop, it is incremented by 2. Finally, effect on the stack pointer is nothing at the end. Anyway, question is not on stack pointer. What is the last one? Halt. So finally, at the end, what is the content of HL parent? It is same number 2095. Because you are done push, you are done exchange, then you are done pop. It is same number. Okay. Just I added space there, 2095 hexa is the content of accumulator. Okay, so 1 hour is over. I wish you all the best. Thank you.